Welcome to the class. Last class we have discussed basics of thermodynamics. So this class we are going to discuss about steam engine. Okay. Now before talking about steam engine, let us see the scenario. See, if you look at this slide, energy consumption around the world and in India. Okay, see here if you look at this graph, here different energy resources are there: oil, coal, gas, nuclear, renewable. Okay, these are different types of energy resources. Okay, so if you look at this graph, oil and coal, people have been using the major energy resources are oil and coal. Okay, now coming to India, so if you look at this bottom figure, so coal is dominating. So coal is the major energy resource. So it is almost about 58.8%. Of course, other energy resources are there, but see, like large hydro, small hydro, wind power, solar power, biomass, nuclear, gas, diesel. Okay, among all these energy resources, coal is the highest around 58.8%. Now coming to worldwide electricity consumption. See here in this chart, according to this chart, so here different countries are there. These are the top 10 countries which are consuming their electricity. See here, so here different countries are there: China, United States, India, Russia, Japan, Canada, Brazil, Korea, and France. Okay, these are the 10 countries which are consuming higher electricity. Okay, in the world. So, see here, coming to our country, India. India is in third position. So, India is in third position. So, this much electricity consumption, kilowatt hour per year. So, it is consuming the electricity from India. Now, coming to our topic, steam engine. Okay, actually, this was the first steam engine. Initially, actually, it's not a steam engine. Here, the idea is uh, by by using steam as a working medium. By using steam as a working medium, we can be done some work. We can create some work. We can do some mechanical work. That is the basic idea here. So the first steam engine is Eolipil or Hero's engine. It is also known as Hero's engine. So actually, it was existing from first century AD. Okay, so you can see in the figure, as you see in the figure, see here it is a bladeless steam turbine. It is a bladeless steam turbine which rotates due to ejection of steam. Okay, so let me explain the setup. So here there is a spherical drum. So at the bottom there is a half spherical drum. Okay, so below the spherical drum there is a heat supply, heat energy. Okay, so it is half spherical drum. It's filled with the water. So from the bottom, so there is a supply of heat energy. Okay, when heat is transferred to the this spherical uh, drum, this water is converted into steam. Okay, but here this spherical drum, this half spherical, so both are attached with the help of the tubes. Okay, both are attached with the tubes. Okay, when this water is converted into steam in the this half spherical drum, this steam passes through the turbine, sorry, passes through the tubes and enters into the spherical drum. Okay, and it comes out, this steam comes out through the this exhaust, so from this side and this side. Okay, because of this steam exhaust, it causes sphere to spin. So this sphere will rotate. So here you can see in this figure clearly. So here how this is spin is rotating. So okay. So as I said here, the basic idea is using steam as a working medium. So some work can be done. So we can create some mechanical energy. This is the basic idea. So from this, people have been developed so many cycles, carnot cycle, Rankine cycles. So nowadays, those cycles have been used in the power plant. Okay. Uh, See here. So in the world, one of the largest steam power plant, that is Taichung Power Plant. So it is situated in Taiwan. So this power plant is situated in the Taiwan. Is situated in the Taiwan. So the it is a coal-fired. Here the energy source is the coal. This is the coal-fired unit. The capacity is 5,500 megawatt. So the capacity is 5,500 megawatt. It has drum-type boiler and single reheat type steam engine. Okay. Coming to India, in India, we have largest steel plant in the state of Madhya Pradesh. In the state of Madhya Pradesh. So here, uh, the name of the steel plant is the name of the steel plant is Vindhyachal Thermal Power Station. Okay. So in our India, where it is in the Madhya Pradesh, the largest power plant. So the capacity is 4,760 megawatt. Okay, actually, it is owned and operated by a NTPC, National Thermal Power Corporation. Now, this application of this steam engine. So, actually, the first steam locomotive. So, actually, it ran between Stockton and Darlington in UK, 1825. Okay, coming to India, the first locomotive ran between from Red Hills to Chinchadripet Bridge in Madras in 1837. Okay, but the first passenger train in India, which ran between Bodibandar Mumbai station and Thane on 16 April 1853. Okay. Now, coming to carnot cycle, I think you already have some idea about carnot cycle. So here, what we discussed in the last class, that was the carnot cycle. Their working medium was gas. So here, the working medium is steam. So that is the difference between earlier class carnot cycle and this carnot cycle. So here, in this class, this we are going to discuss about carnot cycle with steam as a working substance. Okay. Now here, see here, is a schematic diagram of carnot engine. Okay. Now see here different this cycle contains there are mainly four devices: compressor, boiler, turbine, and condenser. These are the four devices in the carnot cycle. Okay. So I think we already discussed about how what are the functions of the turbine, condenser, compressor, and boiler. So let us recall again. Here, the function of the compressor is it compresses the water. Okay, it compresses the water. It increases the pressure from low pressure state to high pressure. Okay, once this water gets compressed, this water enters into the boiler. Okay, okay. The function of the boiler is it converts the water into steam. Okay, once the water converted into the steam in the boiler, the steam enters into the turbine. Okay. Here, the steam expands and it generates a, it do some work. Okay. After expanding in the turbine, the expanded steam enters into the condenser. Here, the function of the condenser is it converts the whole the total steam into water. Okay, and the water again enters into the compressor. So this is the cyclic process. Okay, here the major processes are the first process is process 1 to 2 isothermal heat addition. This is the process 1 to 2. Okay, through the boiler. Okay, here what is happening here? Here heat addition at constant temperature. Okay, when you do heat supply, this water is converting into steam. Okay, next process 2 to 3. Process 2 to 3 is reversible adiabatic expansion in turbine. Okay, so this is a process 2 to 3 with the turbine. Okay, here the steam is expanding isentropically. Reversible adiabatic means also called as a isentropic process. Here the steam is expanding isentropically in the turbine. The next process is 3 to 4. Okay, what is the 3 to 4 process? Isothermal heat addition. Okay, here in the condenser, 3 to 4 process go through the condenser. Here, here there is a heat rejection. So because the steam is converting into water. How it is converting into water? By rejecting the heat from the steam. Okay, but it is heat rejection isothermal. The temperature is the constant. Okay. Next process is 4 to 1. Okay. This is a reversible adiabatic compression. So here process 4 to 1 is the through the compressor. Okay, what is happening here? Here water is getting compressed. So it is here compressing it's a isentropic process. Again, it is isentropic process. It's isentropic compression because it is a reversible adiabatic process. Reversible adiabatic process also known as a isentropic process. Okay. So what are the four processes here? 1 to 2 is the isothermal heat addition. 2 to 3 is the reversible adiabatic expansion in turbine. 3 to 4 is isothermal heat rejection in the condenser. 4 to 1 reversible compression in the reversible adiabatic compression in the compressor. Okay, these are the four processes. Okay, now if you draw on PU diagram all these four processes. Now see here, what is the first process? Process 1 to 2 isothermal heat addition. Okay, isothermal heat addition. So see here, so process 1 to 2 is the isothermal heat addition. Okay, heat addition in the boiler. So what is happening in the boiler? So this water is converting into steam. So this volume is increasing from 1 to 2. Okay, and also here the pressure is constant. Here P1 equals to P2. So that's why it's straight line. Now, what is the second process? Second process is 2 to 3. Reversible adiabatic expansion in the turbine. Okay, here steam is expanding. The steam is expanding, and when the steam expands through the turbine, the pressure decreases. The pressure decreases, and the volume increases. So see here, this is the point 2, 2 to 3. 2 to 3 is the reversible adiabatic expansion. So the volume increases from point V2 to V2 3, and the pressure decreases from P1 to P3. Sorry, P2 to P3. Okay, so this is about reversible adiabatic expansion in the turbine. Okay, now what is the next process? Isothermal heat rejection. Heat rejection in the condenser. Okay, here what is happening? Again, it is a isothermal process, and also here pressure is almost constant. Okay, so here what is happening? So process 3 to 4. So the isothermal heat rejection. So here the steam is converting into water. Okay, So when the steam is converting to water, the volume is decreasing from V3 to V4. The volume is decreasing from V3 to V4. From the V3 to V4. Okay. Now, what's the final process? Reversible adiabatic compression in the compressor. Okay. So, what is the function of the compressor? It compresses the water and it raises the pressure. So, the process 4 to 1. See, the process 4 to 1, the pressure is increasing. So, the pressure increasing from again P4 to P1. Okay. So, the pressure is increasing and the volume is decreasing because this there is a compression. So, the volume is decreasing from V4 to V1. So this is the all four processes on PV diagram. PV diagram. So now coming to TS diagram, temperature and entropy diagram. See, again, we try to draw all these four processes on the TS diagram, on TS temperature and entropy. Here, again, the first process is isothermal heat addition. So since it is the isothermal process, so the temperature is the constant. So 1 to 2 is the constant. So 1 to 2 it is a straight line, straight horizontal line. Why? Because it is isothermal uh, isothermal process. But there is a heat addition. And before, so one point I forgot to tell. See here, there are two lines are there, and this line and this line. So this line is the saturated liquid line. This line is the saturated vapor line. Okay. So saturated liquid line and saturated vapor line. Now, coming to process 1 to 2. What is happening in the boiler? In the boiler, the water is converting into steam. When we adding the heat to the boiler, the water is converting into steam. So here, so this is the saturated liquid line and this is the saturated vapor layer. So here the process 1 to 2. So this water is converting into vapor. So but during the phase change, the water is converting into steam. The temperature will be constant. So actually this is the latent heat. So this is the latent heat. So this region is called saturation region. Okay. I think you already aware of all these things. So this is a saturated liquid line. This is a saturated vapor line. So during the process 1 to 2, the water is converting into steam. Okay. Here, since the temperature is constant, this is the horizontal line. Now, second process. What is the second process? Reversible adiabatic expansion. Reversible adiabatic expansion. So, since it is a reversible adiabatic process also known as a isentropic process. Since it is isentropic process, here entropy is constant. So here there is no change in the entropy. Why? Because there is no heat addition and heat rejection in this process. So this entropy is the constant. So 2 to 3 is the entropy, vertical line. Okay. So we observe here, the point 2 is the steam. Point 2 is steam. So what is happening in the point 2 to 3? It is passing through the turbine. So this is passing through the turbine. So when it is passing through the turbine, the steam is expanding. When the steam expands, so some steam may converting into the liquid. So here at point 3, there will be water vapor mixture. Okay, there will be water vapor mixture. So that's why. So it is inside the saturated vapor line. Okay. Now the next is 3 to 4. 3 to 4. Okay. Now what is happening in the 3 to 4? 3 to 4 is again is a isothermal heat rejection in the condenser. So now isothermal heat rejection in the condenser. What is happening in the condenser? So it is absorbing the heat and it absorbing the heat and this steam is converting into water. Okay. So that's why, but this process is isothermal process. Since it is isothermal process, here 4 to 3 is the straight line. Straight line, but there will be change in entropy because so this steam is getting condensed and converting into the liquid. So there will be phase change. But here still there will be a water vapor mixture will be there. So that is the drawback in the carnot cycle that I will explain in the further classes. So now just assume that here now there is a liquid. The water vapor is converted into liquid. Okay, but this is not actually pure liquid. Here water vapor mixture is there. See, if you look at this figure, so this line is below the saturated liquid line. So here, so definitely there is a water vapor mixture. Okay, but here just assume that it is a liquid. Okay, now after getting condensed, what is the next process? Process is 4 to 1. Okay, in 4 to 1, what is happening in the 4 to 1? Reversible adiabatic compression. So 4 to 1 is the reversible adiabatic compression. So in reversible adiabatic compression, since it is a reversible adiabatic, it is a isentropic process. For isentropic process, again it is a straight line. So this is a straight line. The entropy is constant. Why? Because it's constant. So since it is adiabatic, there will be no heat addition and heat rejection in the compressor. So that's why here entropy is the constant. Okay, this is regarding TS diagram. Okay, and one more thing is here T1 equals to T2. Why? Because T1 equals to T2. Since it is isothermal process, it is isothermal process. Here T1 equals to T2, and also T3 equals to T4. Here also it is, since it is isothermal process, T3 equals to T4. Okay. This is regarding a carnot cycle with steam as a working substance. Now, let us see one by one. Each and every process, let us see one by one. So what is the first process? The first process is isothermal heat addition. In isothermal heat addition, where it is heat, we are adding the heat in the boiler. Okay, so we are adding the heat in the boiler. What is happening in the boiler? In the boiler, the water is converting into steam. Okay, if you look at the TS diagram, so 1 to 2 is the isothermal heat addition. So since it is isothermal, the line is the constant, and so there is a phase change. So this is the saturated liquid line. This line is the saturated vapor line. This line. So there is a phase change from liquid to vapor. So, so since there is a phase change, there will be a change in entropy. I think here entropy, yes, see here entropy, yes, 1. Okay. Now, okay, as I said, when there is a phase change, during the phase change from 1 to 2, from liquid to vapor, so the temperature will be constant. Okay, this zone is the saturation zone. So, and this is a latent heat. This region is a latent heat. Okay, now, so how to find the, here our aim is to find out the heat absorbed during an isothermal expansion. How to find the heat absorption here? See here. So the area under this line 1 to 2. The area under this line is 1 to BA1. So the area under this line is 1 to BA1. So from this area we can find the heat absorbed during an isothermal process. Heat absorbed. So here we are giving the heat. So this is the source. So if you remember the second law of thermodynamics, so this is the source. We are giving the heat here, and there is a heat rejection here. So Q in here, we are giving the heat. Here Q in, here Q out. Okay. Now, see here. Now, how to find the heat absorption? The area under this 1 to BA. From this area, we can find the heat absorbed during an isothermal expansion. Okay. Now, how to find this area? Q1 to 2. Heat absorbed is equals to change in entropy into absolute temperature. Okay. So here changing entropy. So here process is 1 to 2. So the process is 1 to 2. So the change in entropy will be S2 minus S1. So the change in entropy is S2 minus S1, and the absolute temperature. Here temperature is in this process, the temperature is T1. T1 equals to T2. So the process, the temperature is T1. So the total equation is S2 minus S1 change in entropy into temperature T1 equals to, also we can write it as, since here as I said T1 equals to T2, since it is the isothermal process, here T1 equals to T2. So this equation also we can write it as S2 minus S1 into T2. Why? Because here T1 equals to T2. Why it is T1 equals to T2? Here since it is a isothermal process. Okay. This is regarding process 1 to 2. In the process 1 to 2, we learned how to calculate the heat absorption, heat addition in the process 1 to 2. Now, process 2 to 3. It is a reversible adiabatic expansion in the turbine. Process 2 to 3 is the uh, reversible adiabatic in the turbine. That means it is isentropic process. Okay, process 2 to 3. So now this process we are going to discuss. In the process 2 to 3, what is happening? The steam is passing through the turbine, and in the turbine the steam expanding. The steam is expanding, but 2 to 3 is the reversible adiabatic. It is isentropic process. So since it is an adiabatic process, there will be no heat addition and heat rejection in this process. In this process, there will be no heat addition, no heat rejection. So since there will be no change in the entropy, so that's why here this line is constant. There will be no change in entropy. This line is constant. So here this is the S2, this is the S1 entropy. Okay, so there is no change in the entropy. Now coming to process 3 to 4. In the process 3 to 4, what is happening in the process 3 to 4? Isothermal heat rejection, where here it is getting rejected in the condenser. Okay, so 3 to 4. So now we are going to discuss about 3 to 4, this process. So in this process, what is happening here? Here also, this is also isothermal process. Since it is isothermal process, your line is the horizontal line. But here, this mixture is getting condensed to 0.4. So definitely there will be change in the entropy. So there will be entropy change from S2 to S1. Okay. Now, uh, here also we have to find out how much heat it is rejected. So here, this process is 3 to 4 processes heat rejection in the condenser. Okay, so that we have to find out in the here in the condenser how much heat it is rejecting, how much is rejecting in the condenser. That we are going to find out here. How to find out? Again the same procedure. So the area under this 4 3, the area under this line. So what are the 4 3 B C? So here 3 4 B A. This area, from this area we can find the heat rejection during isothermal compression. Okay, how to find this one? So change in entropy into absolute temperature. Okay, so during the process 4 to 3, so changing entropy is S2 minus S1. Okay, so S2 minus S1, and but temperature, what is the temperature here? So the process is 3 to 4. So since it is 3 to 4, the temperature is T. So T3, here T3 is there. Okay. Now, but since it is isothermal process, here T3 equals to T4. So that's why we can write this equation into in terms of T4, S2 minus S1 into T4. Okay. So this is the way we can find the heat rejection in the process 3 to 4. Okay. Up to now, what we discussed it in the heat addition in the process 1 to 2 and 2 to 3. 2 to 3, since it is a isentropic process, definitely the entropy is constant. There will be no change in the entropy. And the next process is 3 to 4. 3 to 4 is the isothermal heat rejection in the condenser. So here we have to find out how much heat is rejecting inside the condenser. So that is that we are finding by using this formula. Now, the last process is process 421, reversible adiabatic compression in a compressor. So the final process is 421. Okay. So see here, what is happening here? So the in the process in the compressor, so the liquid is getting compressed. In the compressor, the liquid is getting compressed. When the liquid get compressed, the temperature will increase. So the temperature is increasing from T3 to T1. Okay. But here, see here, this mixture, this water vapor mixture, it is converting into liquid. Okay, but here actually there will be water vapor mixture that I will discuss in further classes. Just assume that here there is a liquid, pure liquid. Okay, this condensed liquid sending uh, to the turbine. So 1 to 2 is the turbine. Okay, process 1 to 2 is the turbine. So 4 to 1 is the compressor. So what is happening in the compressor? 4 to 1, the water is getting compressed. That compressed water enters into the turbine. 1 to 2 is the turbine. Okay. Now here what we are discussing about the process 4 to 1. Okay. What is happening? What is the process 4 to 1? It is the reversible adiabatic compression. So since it is a reversible adiabatic, it is an isentropic process. So since it is adiabatic process, there will be no heat addition and heat rejection. So definitely there will be no change in the entropy. So entropy will be the constant. So that's why here 4 to 1 is the constant line. Okay. Now, okay. Now we all discussed about we are now we discussed all the process 1 to 2, 2 to 3, 3 to 4, 4 to 1. So we discussed all the processes. So now the cycle is completed. Okay. Now what we have to find out? Work done during the cycle. So during this total cycle, what is the work done? Okay, that we have to find out. How to find out? Heat absorbed minus heat rejected. Okay, where it heat absorbing, where is the heat addition? Heat addition at 1 to 2 and heat rejection at 4 to 3. So where we are giving the heat, we are adding heat at the boiler. Why we are adding? To convert the water into the steam. Okay, so that's why 1 to 2 is the here this in this process heat absorbed and heat rejection. Where is heat getting rejected? Heat is getting rejected in the condenser. So what is happening in the condenser? In the condenser, the steam is converting into water by losing the heat. Okay. So that's why 4 to 3 is the heat rejected. Okay. 1 to 2 and 4 to 3. Okay. Now substitute. Uh, we know these equations. How to find the heat addition at process 1 to 2. How to find the heat rejection at process 4 to 3. So these equations we already discussed. So once you substitute all these two equations, heat absorbed is S2 minus S1 T1. So the change in entropy S2 minus S1 here S2 here S1. Okay, 1 to 2 process 1 to 2 is the change in entropy S2 minus S1 into the temperature. What is the temperature in process 1 to 2? T1. The temperature is T1. So that's why here T1. Okay. Now minus heat rejected. Where heat is getting rejected? In the process 3 to 4. In the process 3 to 4 in the condenser, the heat is getting rejected. Here, how to find the heat amount of heat rejection? So here again, change in entropy S2 minus S1, S2 minus S1, and temperature in the process 3 to 4, the temperature is 3 P3. Why? Because it is here temperature is isothermal, constant temperature. So it is P3. Okay. Now if you simplify this above equation, the final equation is S2 minus S1 into T1 minus T3. Okay, this is the final equation. From this equation, we can find the work done during cycle. But to find the work done, what are the inputs we required? Entropy S2, entropy S1, and T1, final temperature and after heat rejection, and T3, the temperature after rejection, and T1 at the heat addition. So once we know the T1, T3, S2, S1 values, we can find the work done during the cycle. Okay. Now, efficiency of the carnot cycle. So what is efficiency? Generally, how we find the efficiency? Output by input. Here output, what is the output? Work done. Okay. The work done is, what is the work done here? S2 minus S1 into T1 minus T3. So we already, we know how to calculate the work done. We discussed here S2 minus S1 into T1 minus T3. So work done is S2 minus S1 into T1 minus T3 divided by heat absorbed. What is heat? Where heat is getting absorbed? In the process 1 to 2 in the at the boiler. So S2 minus S1 into, here the temperature is T1. So okay, so once you substitute everything, once you simplify this equation, you will get T1 minus T3 divided by T1. Okay, this equation we also can write like this: efficiency equals to 1 minus T3 by T1. Okay, here T3 is the low temperature. Is the low temperature. This is the high, is the T1 is the high temperature. T3 is the low temperature. Why low temperature? Because here getting heat is getting rejected. So at the T1, heat is getting added. There is a heat absorption. So, so if you look at the, if you remember that second law of thermodynamics, so here T3 is the sink. So T1 is the source. Okay, source, reservoir, and sink. Now, here I think this point I already explained. What is T1? Highest temperature corresponding to the boiler pressure. So at the T1, here we are giving the heat addition. Okay, here temperature will be higher at the boiler. Where will be lower? Lowest temperature corresponding to the condenser pressure. So in the here in the condenser T3, the temperature is lower, and also here if you remember the PV diagram, P1 equals to P2, P3 equals to P2. Okay, so this is regarding Carnot cycle. This is the Carnot cycle. Here working medium is the steam. Okay, that you remember. Now let us solve problem. See here, let us read together. In a Carnot cycle, heat is supplied at 350 degrees centigrade and is rejected at 25 degrees centigrade. Okay. The working fluid is water, while while receiving heat evaporates from liquid at 350 degrees centigrade to steam at 350 degrees centigrade. From the steam tables, okay, regarding steam tables, how to see the those things, so I will discuss in the next class. From the steam tables, the entropy change for this process is 1.438 kilojoule per kg Kelvin. Okay, if the cycle operates on stationary mass of 1 kg of water, find the heat supplied, work done, and heat rejected per cycle. Okay, so for your reference, I have given PS diagram also. I think all of you you have notebooks with you. Just I'm giving 2 minutes time. Everyone note down, just write down what is the given data and try to solve the problem. I'm just giving 2 minutes. Try to solve the problem. Later we will solve together. Okay, I'm giving 2 minutes. Try to solve. Just try to write a given data. In every class, all of you, along with this video lecture, keep with your notebook and write your running notes. So let us solve it together. In carnot cycle, heat is supplied at 350 degrees centigrade and rejected at 225 degrees centigrade, which means heat is supplying, where we are supplying the heat supplying at the boiler, the process 1 to 2. So this is the P1. Okay. Now, and the heat is rejecting. Where is getting heat getting rejected? Heat rejecting at the condenser. So here, this the process 3 to 4. Here in this process, the heat is getting rejected. So here, this is the temperature P3. Okay. Now, the working fluid is water. Here, working fluid is water. Thus, water is converting into the steam in the boiler. Which while receiving heat evaporates from liquid at 350 degrees centigrade to steam at 350 degrees centigrade. So this line is very important. So this evaporating from liquid at 350 degrees centigrade to steam at 350 degrees centigrade. This point already explained. During the phase change from liquid to steam, the temperature will be same. So that's why here, so 350 degrees centigrade and 350 degrees centigrade. So at a constant temperature, there will be phase change, the liquid to steam. From steam tables, the entropy change for this process is 1.438. Entropy change. What is the entropy change? So this is the S2. This is the S1. So entropy change is S2 minus S1. Okay. The entropy change is 1.438. Okay. The other data is if the cycle operates on a stationary mass of 1 kg of water, find the heat supplied, work done, and heat rejected per cycle. Okay, what we have to find out? Heat supplied, where we are supplying the heat at the process 1 to 2 at the boiler. We are always supplying the heat at the boiler to convert the water into the steam. Okay, so 1 to 2 is the heat supplying, and work done. Where is work done? Done happening. So when steam passing through the turbine, so it is giving some work. It is producing some work. There will be mechanical energy. So near the turbine, at the turbine, there is a work done, and heat rejected. Heat rejected per cycle. Where is heat is getting rejected? Heat is getting rejected in the condenser. Process 3 to 4. During the process 3 to 4, in the condenser, the steam is converting into liquid. So in the process 3 to 4, heat is getting rejected. So this is the given data. Okay. Now let us solve it together. See. So the given T1, T3, and change in entropy S2 minus S1. Okay. Here they given in the degree centigrade, 350 degrees centigrade. Just convert into Kelvin. How to convert into Kelvin? Plus 273. So when you add 273, it will convert into Kelvin, 623 Kelvin. Same way here in the T3, 25 degrees centigrade. The 25 degrees centigrade, if you want to convert into Kelvin, add 273. So 298 is the Kelvin. Okay, T3 value. And the change in entropy, they are already given. 1.438 kilojoule per kg Kelvin in the problem. Now, what is the first question? Heat supplied per cycle. Okay. So, if you look at the TS diagram, where we are supplying the heat, we are supplying the heat at the boiler, the process 1 to 2. So, here, so Q equals to this equation we already discussed. What is the equation? Here, change in entropy is S2 and S2. Okay. So, the change in entropy is S2 minus S1 into, and this process is 2 to 1. So, 1 to 2. So, that's why is the T1. Okay, from this equation, we can find the heat supply. So, in the problem, they already given S2 minus S1 value. What is S2 minus S1 value? 1.438 into T1. What is the T1 value? 623. So, T1 value is 623. So, once you substitute here, you will get the heat supplied. Heat supplied in kilojoules per kg. Okay, heat supplied at the boiler in the process 1 to 2. Now, work done. What is the work done? So, this equation, work done during the cycle, S2 minus S1, T1 minus T3. So, this is the work done equation. So, S2 minus S1 already given, and T1, T3 values we know. Just substitute all the values, you will get the work done per cycle. Okay. Now, next one is, final one is heat rejection. Where heat rejection is happening in the condenser. So which process? 3 to 4. 3 to 4. In the 3 to 4, the water is getting condensed. Okay. So here again, so from this equation also we know S2 minus S1 into P3. So this equation we already discussed in the previous slides. The same equation I'm using here. But where is heating? You should remember where we are adding the heat, where we are rejecting the heat. We are adding the heat at the boiler to convert the water into steam. And the heat is getting rejected. Where is heat is getting rejected? Heat is getting rejected in the condenser. In the condenser, the steam is converting into water. Okay. So now heat rejected. How to find the heat rejected? Change in entropy S2 minus S1 into T. We know the value of change in entropy S2 minus S1, and we also know the value of T3. Just substitute all the values, we will get the heat rejected. Okay. Today we discussed about the carnot cycle. We are working with first you remember the carnot cycle with the steam as the working medium. Okay, and also we solve some simple problem. So next class we will discuss about Rankine cycle. So this is the Rankine cyclist. The Rankine, what it is here, as I said, here in the point 4, there is a water vapor mixture. So it's not fully water. So when we get the water, once this line extended to the this saturated liquid line, then only we'll get the water. So that modifications of Rankine we done. So then the Rankine cycle came into the picture. That is the Rankine cycle that we will discuss in the next week. Okay. Thank you. With this site, I'm stopping here. Okay. Thank you.